Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. This is the HAROGIC SAE-200, a 20 GHz real-time spectrum analyzer with FPGA-based signal processing to give you that really fast sweep speed. And this has 100 MHz of analysis bandwidth, USB-C powered and operated, and it is absolutely tiny. So there's a lot to talk about because I want to take it apart and see how they've squeezed all the functionality into this form factor and then do a whole bunch of experiment with it. Let's get started. And here's the HAROGIC SAE-200 20 GHz real-time spectrum analyzer, and it is tiny. It's so great to have such a small form factor because you can stack them, you can squeeze them into tight spaces. It's almost pocket size. So I really like that. Now looking on this side, here's the main input. We have a K-type connector. That's the only RF input in the front. Now you will have to be careful because the full-scale input range of this is a little bit more limited than some of the other traditional spectrum analyzers. 23 dBm is the maximum input when the amplifier is turned off, and 10 dBm is the maximum when the preamp is on, which is probably the damage level of the preamp. Now we do have also a 12-volt maximum DC input, most likely because of the type of decoupling capacitor they use, the DC block they use in the front end before their main circuit. So yeah, tiny form factor here. We do have some openings here for fan. There is definitely a fan inside of this. And in the back, we have a few interfaces. So this thing runs completely from USB-C, which is great. We do have a power and a data. They're separate from each other. Several reasons for that, because it allows you to separate completely the power management also from the data port, and it does have the screws for securing that. So that's a nice touch there. If you have the right USB cable, you will be able to secure it nicely. Some fans over here. And then we have some auxiliary IOs and another connector at the top for some expansions and passing different type of GPS signals in and out, which is also nice. So yeah, they fit everything into this absolutely tiny form factor. But I really want to take it apart completely and analyze the circuit and actually understand how they've managed to compress all of that, including the pre-select filters, synthesizers, digitizers, FPGA, everything into this. Let's take a look. Now, as with any miniaturization and cost reduction, there will be compromises to the specification and the performance we need to keep in mind. So let's take a look at the data sheet to make sure we're getting what we're expecting. So for phase noise, a single sideband phase noise, let's say at a carrier of 1 GHz, offset of 1 kHz, we should be getting minus 91.2 dBc per hertz. We're going to test that. And at further carrier offsets, it's going to get better as to be expected. Now at 20 GHz, it goes down to minus 80.6 dBc per hertz, and that's somewhat to be expected because, of course, the performance of the internal synthesizers are going to get worse. There will be multipliers inside the synthesizers to achieve this wide range, and that's going to degrade that. So that's okay. Now, in terms of the spurs, this is pretty important if you're looking for very, very small signals. Now, for most users, spurs of minus 90, minus 80 dBc with respect to the carrier, I mean, that should be okay. This is with respect to the actual reference level, actually. So yeah, if you're looking for a signal that's say minus 90 dBm and you're looking at a 0 dBm reference level, it would be difficult to tell what's a spur and what's real. But for most people, that's probably okay. Especially if you're not doing over-the-air testing, this probably doesn't affect you so much. Image rejection is going to be good at low frequencies, and at high frequencies in here, it says that you will still be able to get 90 dBc typical if the enhanced mode is turned on, and if not, it will be 60. I suspect what they do here is that in the enhanced mode, the sweep will be slower, and it will do multiple measurements and try to get rid of its own internal spurs. That would be my guess. It's kind of like a software pre-selector and image rejection. So that we'll take a look at that as well. Going further out, IIP2 and IIP3 are pretty important. Now, IIP2 is going to be really good for these architectures, as you can see. But the IIP3, so at 1 GHz, they're saying you should be able to do 45.5 dBm, which is really good. That's with a 20 dBm reference level, probably at the highest attenuation. And it goes down about 20. So you can see the delta between these two is exactly the delta here. So I suspect it's just an attenuation difference. So we're going to have to check this and see what it looks like. It does get worse when minus 20 dBm is on. That's most likely because the front-end preamp will be selected. So you do need to keep this in mind if you do intend to measure OIP3, and we will try this out too. Now going further in here, amplitude accuracy plus or minus 2, plus or minus 3. That's really important to keep in mind. Ultra high performance spectrum analyzers will be plus or minus 0.4, 0.5, but for something this small, again, for majority of the users, this may not matter, but for absolute power measurements, this is of course going to give you a wide error as to be expected. And then let's see what else is in here that might be interesting. Displayed average noise level are shown here. Yeah, some of these numbers are really, really small, minus 165. So we can try that. That's, of course, with minus 50 dBm reference level, meaning the highest level of preamplifier selection and the lowest level of resolution bandwidth. So that should be something that we can check. Everything else looks like about okay. We do have about, let's say, 1.1 terahertz per second of sweep speed for resolution bandwidth of more than 1 megahertz. which is just basically capturing very quickly in 1 megahertz. That's not that difficult to do. And then, yeah, the rest of it, some specifications on the IQ sample rate. It does have a 100 megahertz of analysis bandwidth, so they must be running their ADC at a fairly high rate. Yeah, you can see, there you go, 8 nanoseconds is the lowest time resolution, 100 megahertz maximum. A couple of different detector types done all in software, of course. FFT analysis is mentioned. Yeah, it's a fairly comprehensive, and they certainly have paid attention to the details of how to write a proper data sheet and so on. So we'll check some of these. It's always good to take a look at it. So let's do a detailed teardown and see exactly how they've put this system together, because from a spectrum analyzer point of view, this type of miniaturization is not easy. You have to solve thermal problems, RF isolation problems, power deliveries, and so on. So I'd like to see how they've done that. So removing the top covers, you can see how many different boards there are and how nicely they meet together. So there's a lot of mechanical board actually that's gone into this. So this heatsink is just attached to the top here, and air is supposed to flow over this. So the thermal of this is probably okay. We'll see how hot it runs. But yeah, there are a lot of different boards. Clearly, the power distribution board you can see is separate. And I'm interested in seeing how they've divided this a little bit further up. So let's do a complete teardown. So the thermal consideration of this device is a little bit of an afterthought. The heatsink is attached with a thermal pad on top of here, assuming this is where the majority of the thermal load is, although this whole thing is fairly well coupled together because of all the metal. And then this is glued on top. In reality, if you wanted to design this from scratch, you would put ridges directly into the machine chassis, and then the fan would have standoffs here blowing across it appropriately. Most likely the thermal was a little bit something they decide afterwards, but I guess this works. Alright, after removing dozens and dozens of screws, I've managed to completely take this thing apart, and we're going to take a close look at it. I do have to say I'm impressed with the amount of work that's gone into miniaturizing and actually building these stacks of PCBs, because they plug into each other back and forth and signal is sent all over the place. There is a ton of mechanical, actually precision mechanical, that goes into it because everything is so small. They even have little tiny patches that cover all the screw holes so nothing touches the PCBs. Each of these individual PCBs are attached with multiple screws on both sides to the actual chassis, separating the different compartment, which is very important for isolation. Putting a lot of screws means a lot of work in assembly, but at the same time, that's what you have to do if you want to get the best performance out of this. There are multiple main PCBs that all interact with each other. Some of them are dedicated for the digital power and, of course, the RF front end. So let's take some high-resolution photos and go through it. So now let's take a look at all the individual boards so we can get a general understanding of the architecture of the instrument. This is the RF front end, top of the board, and the bottom of the board, which is mirrored. This is the RF input. You can see the pin over here. This pin goes into an external connector, which is mounted mechanically to the chassis of the instrument. That's where you get the stability of the connector itself. You can also replace that connector fairly easily if it gets damaged. Now the RF input coming over here, there's a DC block in its way, and then immediately there is a switch. This four-way switch allows you to switch the front end into a preamplifier if you want for, let's say, very low noise figure, or you can bypass the preamplifiers. Now this, because it's a four-way switch, also allows you to select different preamplifiers in different bands, so you don't have to have one that covers the entire frequency range, which is, I think, what they've done here. So for example, this component over here, this is a 6 to 26.5 gigahertz amplifier, actually has a noise figure of about 2.5 dB. Implemented in gallium arsenide PHEMT from Hittite. And then on the other side, I think there's another preamplifier over here. And then the other signal out there, I think it goes into this component, which is a 100 megahertz amplifier. It looks like in this architecture, for input frequencies below 100 megahertz or so, they're probably digitizing it directly because you don't want to pass that through the mixer. You probably have an ADC that can just digitize it raw, so you don't have to do anything else with it. Now you can see these signals all join back over here into this one, perhaps with the exception of this one. And they go through this component over here, which is a programmable broadband attenuator. So basically anything going through over here, you can now adjust the amplitude of. If you don't want any preamplification at all, you simply go through this path, which makes sense. Now notice how this attenuator is before any of our preselector filter. Now there are advantages and disadvantages to that. If you put it after, you're going to have to deal with having multiple of them potentially, but it's really a choice of the architecture. Now if you notice, there are a lot of filters over here. It's also interesting that they're using ceramic filters as an individual component to be soldered onto the board rather than implementing their filters directly into the PCB. This is more expensive in some ways because this is a more expensive material. You can get higher quality filters this way, but then the PCB becomes perhaps cheaper as a result of that, although you still have to process all this high frequency stuff on it anyway. Interesting choice that they've gone with this, especially with this really large one. They just simply drop in. All of these are pre-select filters. You can see individual filter paths among all of them, and the size of these filters are much smaller than the size of these ones, and that should tell us that These are the higher frequency filters. And each of these filter banks is accompanying with a whole bunch of switches in order to accommodate, of course, all of the different selection paths. Same as this one, this has many more paths, in fact, more and more filters over here. On the other side, you can see some of the filters bands are lumped. And we see this quite often as well. At some point, these hairpin filters just simply become too large. And you can just do this with lumped LC component, which is exactly what's going over here. Interesting also that there's a hole here in the PCB. I wonder why they've done that. Maybe they were looking for a different component initially. Not sure actually, because the back of this ceramic piece is ground anyway, so I'm not sure why they have that. And then on the other side, you have another amplifier over here. This is about 7.5 to 26.5 gigahertz. So clearly, this is one RF band after pre-selection. And then on the other side, you have the lower frequency things with filters and amplifiers and attenuators as well. And then you get this one, which must be the lower frequency version. So what comes out of this board are still RF inputs. In fact, these RF signals are basically the same as the input, except pre-selected, attenuated, and amplified. There is no frequency conversion at all on this. And on the other side, there is some more filter over here, some more switches over here. Nothing really unusual going on here. So it's interesting that this front end then can be optimized and more filters can be changed without affecting the rest of it. The frequency conversion all happens somewhere else. Now, one thing that did occur to me is that sometimes you may want to have a hole in the PCB just to prevent some kind of a substrate mode from propagating, improving the isolation between various traces. Interestingly enough, I don't see a lot of via stitching unless all the vias are buried and you can't actually see them, which would make this process, this PCB process, quite a bit more expensive. But yeah, having said that, this hole is obviously a lot smaller than this substrate over here, but it can potentially improve some isolation techniques. Now, on this second RF board, things begin to become interesting because this is the first time we're going to see our frequency conversion. Now, the overall architecture of the spectrum analyzer is going to be super heterodyne, as it is very common with these type of instruments before they are digitized. So remember that from the previous board, we had a high band and a low band output. The high band was going through the pre-selectors and the upper frequency ranges, and the low band would go all the way down to near DC. And those two both enter this board. So here's the high band one. Coming over here, you can see it enters this component, and this is a Hittite or Analog Devices 6 to 26.5 gigahertz mixer. Now, interestingly enough, this is an IQ mixer, and they seem to be somehow combining the IQ into some kind of a LTCC filter or combiner of some kind, which is interesting because they're certainly not keeping both of them. Now, on the other side, we need an LO for this mixer, and there's the 20 gigahertz synthesizer in here. The output of that goes through some filter as well, some amplifier, perhaps some more filtering, and then a medium power amplifier to drive the LO, to make sure that the LO is strong enough as required by these kind of mixers. And the output of this finds its way into this port, which is our unified IF port, and that's going to go into the next port for another down conversion, as we will see. Now, on the other side, the low frequency quote-unquote part comes yet into more pre-selector filters. So there's even more of them. I guess they couldn't fit that onto the other board. And there's switches on each side for selection. There's another pair of switches in here. And I think this is just a gallium arsenide amplifier in the middle to give you some boost of gain if required, so you can switch it to the gain path or not. Now, in the middle over here is another mixer. Interestingly enough, this mixer is bidirectional, so it can be for up or down conversion. You can see its IF port is differential, and there's a balun in front of it. And the LO is coming back down from here. This synthesizer has two outputs, so one of them is driving this one, and the RF comes from here. Now, I think that, well, I'm not 100% sure, but it could be that they're using this sometimes in up and sometimes in down conversion, because remember what this is supposed to do. All of these frequencies coming in are going to mix with this, and they're going to mix with this. And the combination of the different pre-selector bands and the inputs all have to land within a certain IF frequency, which is required here. Whatever frequencies you put this IF into is going to go into another down conversion stage, except for the very, very low frequencies, where basically there is no mixing and it straight away finds its way into this output. Some more kind of switches and filters and amplifiers in here. On the other side, you can see we have another path that you can select, perhaps from some additional amplification. Nothing else is going on. Some more lumped LC filters in here. So this is many, many bands again. The same hole is present here, perhaps for the same reasons. But yeah, it's interesting. So they're doing some bunch of clever switching between different bands. Again, quite common for this type of architecture, but it allows you to create a unified IF, and that's what we need to remember here. So some IF frequency for the super heterodyne, and some low frequency IF for direct digitization. And finally, here's our mixed signal board where the digitization happens and the final down conversion of the IF stage. So here's the unified IF coming in, again, some switches and filtering, the usual stuff coming in over here. And that has to reach a mixer ultimately for the down conversion, or it has to go to the digitizer directly. There are two synthesizers over here. Both of them can work up to 6.25 gigahertz. Now, I believe one of them is used to provide the LO for the final mixer, and the other one is probably the clock for the ADC. So that maybe is this one going into this. Here's our ADC. This is 12 bits up to 250 megasample per second from ADI, and here's all the differential LVDS lines going into the next board, which is going to capture all that data and process it. This is a programmable RF attenuator, and on the other side, directly underneath it, is our mixer. This works from 400 megahertz to 3.8 gigahertz or so. So the combination of this mixer over here and the digitizer directly and the IF, everything will then get ultimately down converted within the bandwidth of the ADC, and that should take care of everything else. Here's our main core synthesizer. That's going to generate all of our references and everything else going into the rest of these synthesizers as well. The clock is 10 megahertz and 125 megahertz. Crystal over here, the VCO, and there's some additional auxiliary IOs. These are hand soldered, and unfortunately I only saw this after I closed it. They go through so much trouble making these beautiful boards, reflow them, but the things that are hand soldered, it shouldn't look like that. This is such an easy thing to avoid and not have these potential cold solder joints in here. So unfortunately, I've closed mine all the way, otherwise I would have fixed it. There seems to be some more filters over here, nothing unusual, some unpopulated parts, perhaps for some other variants of this board. And over here, this is an Altera 10 a PLD, programmable logic device, Max 10 I think they call them. These are non-volatile, so it has memory and everything else. Is probably working with this ARM processor in conjunction. Here's the crystals and everything else for the ARM. Yeah, that covers everything else. So what comes out of this are basically now fully digital, and this is not an RF circuit anymore on this except for this down conversion. Yeah, looks pretty good. One other interesting thing in here, they actually have a cutout in the board, and they're pushing this VCXO down into the board a little bit with a tiny daughter board in the back and then soldering it. I think they're only doing that to reduce the height of this so that it fits within a certain form factor. That's a lot of trouble to do this, but I admire the creativity to do this little mix here. And yeah, looks pretty interesting. Good way to reduce the height of the overall board. And the final board here receives all of the LVDS data from the ADC and controlling everything else, going into a Cyclone 4 FPGA from Altera, and then some DDR memory in here to store and process, and then some USB controller, and then out into your computer. And the rest of them are power, nothing unusual. Yeah, tiny little board with this FPGA on it, and this is probably where the majority of the heat from this board at least comes from, and that's where the heat sink is actually sitting on top of this. Some programming ports and LEDs and everything else on there. But yeah, there's obviously a lot of code in here to be able to do everything else and packetize everything and send it over the USB. But once the data is digitized, it's just a matter of writing the protocols for a USB interface. Now, before I forget, there is one other tiny little board as well, which is the power board, and this is where the power delivery actually happens. It's nice that this is an individual board because this is a switching power supply, so it's definitely separate from everything else. It's clever to put it like that, and then the power goes through here onto the board at the bottom and gets fully distributed. So the power supply is basically coming through here. It's nice and modular. And so if you now draw that architecture out, it's going to look something like this, somewhat simplified. RF input coming in, the switches for the preamplifier selection, and then all of our pre-select filters, a huge bank of them with an attenuator in the front. Our first mixer, bandpass filtering. Our second mixer, which brings everything down into the frequency range of the ADC. And you can see that signals goes over here, some IF amplifier gain control, and the ADC can then select low frequencies directly digitizing, mid frequencies coming directly from the super heterodyne, and then there is an analog IF output as well, so you do actually get that signal. So you can digitize it externally as well. Quite nice to have this option. It's very valuable if you want to look at something, let's say, broader, or if you have a system that can sample faster, for example, would be quite useful. And the rest is FPGA, DDR, and then USB. Yeah, so this is the overall architecture. Obviously heavily simplified, but it matches what we talked about. So our first test, let's do something simple. We're going to take the Signal Hound phase noise reference clock generator, which is a 1 gigahertz tone at 10 dBm. We're going to feed that into the spectrum analyzer directly. This is an exceptionally clean tone intended for characterizing phase noise. It's lower than most, spectrum analyzers out there. So by this way, we can take a look at the software. We can also see how this guy handles various phase noise measurements. Let's give it a go. And here's the instrument GUI, which you can freely download from their website, and they're updating it periodically. I just downloaded the latest version, which is this one over here. It's nice that it's available and gets upgraded, of course. And there are a lot of features and options. You can pretty much adjust anything you want from the instrument's point of view, including how the digitization is done, which is fantastic. It runs really, really fast, and it's a small software, which is exactly what we were looking for, and it actually has an executable. You can just directly run it. Now, when the instrument is preset, it goes into these settings. You can see it's sweeping from 9 kilohertz to 20 gigahertz, just over 20 gigahertz, running at 447 gigahertz per second. And this is on the spur rejection being standard. If I bypass the spur rejection, you can see that we get quite a bit of speed back, now over 1 terahertz per second. And if you put it into enhanced spur rejection, it slows down. So it's consistent with what we thought, that it's basically making multiple measurements and trying to figure out where the spurs are and getting rid of them. So let's leave it here on standard. Now, one thing that's important is that on an instrument like this, especially with reduced input power capability, you have to make sure that the preamplifier is not on auto on startup. It should always be on forced off, because the instrument should prioritize protecting its input over, let's say, the low noise, because any user can certainly change that. And we'll play around with the reference level and see what it does. Right now, obviously, there is nothing connected to the input, but let's measure our 1 gigahertz reference. So here's the input applied, and you can see there's a lot going on here. So let's think about what's happening. Let's do a peak search. So the signal is at the right frequency, but the power is completely wrong. And that's because we're overloading the input of the spectrum analyzer. And nicely enough, it tells us that, so that you can know and you can adjust your attenuation level. Sometimes these type of spectrum analyzers don't even tell you. And that's pretty bad, because then you would never know you're making the wrong measurement here. We can fix this by just changing the reference level to 10 dBm. And then this should go away, and it does. And then you can see we're reading around 9.5 dBm, which is correct. And at this scale, the frequency 1 gigahertz, this reading is also correct. There's also a lot of additional tones here, but don't worry, these are not from the spectrum analyzer. They're actually coming from our 1 gigahertz reference. I've already verified this with other spectrum analyzers. This is a very good phase noise source, but it doesn't necessarily have a lot of spectral purity. So this is coming from however it is generating that 1 gigahertz tone internally. Harmonics are all correct. That looks good. Now, we know that this instrument has a lot of pre-select filters, it has attenuation in different bands, and it's going to do things differently depending on the frequency span it's sweeping. And therefore, it's trying to find relationships between attenuation and reference level, and I think it's doing that in a somewhat confusing way. For example, I have a reference level at 10 dBm, attenuation is -1. Let's say I want to add 1 dB of attenuation. If I do this, it just changes the reference to -10. So I'm not a big fan of that, because normally you want to have complete control independently, but it's trying to couple them together. Some firmware revision would help this a lot. So if I go all the way up, you can see I can go to 2221 or 22 dB of attenuation, and the reference level maximum in this situation is 12. So if I try to enter 20, it doesn't let me, and then it changes the attenuation to -1. So yeah, that relationship definitely needs some work. Now I can go under system and go into professional mode, which gives me a little bit more control, and I can change the gain strategy for low noise or high linearity. So let's say I want high linearity, but it still doesn't let me do anything about that. And you can see it's still, and I can change the IF gain, which is nice. But then, yeah, this still does this. So they definitely need to fix this, because it's just confusing and can cause user error. So now let's focus around our 1 gigahertz tone and see the attenuation differences there. So interestingly enough, now with -10 and 0, I'm actually reading the right value. So it is definitely confusing what it's doing. So let's set the center at 1 gigahertz here. Let's look at a span of, let's say, 250 megahertz. Okay, so that's our tone. We can do a peak search. It is reading the right value, even though I'm at -10. So let's increase that. So now I can actually do 20 dB. As a reference, and it's high linearity, so I'm not sure what this attenuation is doing. Yeah, it's doing still the same thing. This is quite non-intuitive to me of exactly what is this attenuation and where it is applied. Maybe a block diagram where it is applied directly in the GUI would actually be quite helpful. But anyway, let's set this to a 10 dBm input. Let it choose everything else, and that's all correct. Well, now let's measure the phase noise of this, because it should be now the phase noise of the spectrum analyzer, because the source is extremely clean. And we can do this because it does have a couple of different modes that we can go to, but it does also have a couple of different measurements. Here you go. So here's a measurement, a few different ones, and phase noise is in fact one of them. Okay, let's select that. So we're starting from 100 kilohertz offset to a 10 megahertz, 100 hertz to 10 megahertz, and the frequency it already has picked up. Everything else is done. Yeah, it does it pretty well actually on its own. Did it change anything with this? No, it's still correct, and it is peaking. Let's see if it's peaking that. Yeah, it's peaking the value correctly as well. And here's our marker. So we can put our marker at a 1 kilohertz offset, we're at minus 96, so better than the specification. If I'm not mistaken, the specification at 1 kilohertz offset is supposed to be minus 91, so it is definitely doing better than that. And we can go to a 10 kilohertz is minus 103, and at 10 kilohertz should be minus 99. Yeah, so pretty good. And it should be about the same at 100 kilohertz offset, and in fact it is. And at 1 megahertz offset, it should be about minus 122. What are we saying here? Yeah, it meets its spec. Pretty good. So at 1 gigahertz, indeed, it does have a very nice, well-behaved frequency response in terms of the phase noise response, I should say. Yeah, pretty good. So let's try and measure some spurious tones. Now, in order to measure the spectrum analyzer's performance, we need to generate a perfectly spectrally pure tone with no harmonics. And I'm doing that by using a Rohde & SMW-200A. This is a 2-channel instrument. I'm using 1 channel here, and I'm just using 3 gigahertz as one example. 0 dBm coming out. Now, despite the fact that this is already very clean, we really want to filter it even more. So I'm passing it here into a bandpass filter. This is a tunable bandpass filter set to 3 gigahertz already. It has a rotation knob here in the front. And I'm taking the output of that and connecting it here to the Rohde & FSW. We're doing this just to get a reference measurement because this is a YIG pre-selected instrument and it's going to be extremely clean. So let's take a look at it. And here's a reference tone, and look at that. We're looking at 3.2 gigahertz. I set it around there to get them best out of the filter, and it's sitting at 0 dBm with a marker right over here. And look at the second harmonic here. It's more than 90 dBc down. So this is extremely clean from DC to 20 gigahertz. So this would be a very good reference input. Now you also want to make sure there are no spurs around it because we're looking at it from so far away. We can definitely verify that as well. Set the frequency to 3.2 gigahertz as the center. And then let's reduce the span to something like 50 megahertz here. We can reduce the bandwidth even lower. And look at that. I mean, that's as clean as it's going to get. Signals around 0 dBm. So that should be not surprising because we're taking this from an SMW-200A, filtering it, and of course the FSW is going to give us a really good spurious dynamic range. Now let's try it with the SAE-200. And here's that setup. Exactly the same idea, except now the output of the filter is connected to the SAE-200. So here's our signal. You can see the amplitude is correct, and on a full span from DC to 20 gigahertz, it's doing a very good job. You can see the second harmonic sometimes captured here. The other instrument does a better job at capturing a very small signal consistently, but yeah, it is certainly doing that. Now, if you look closely near the actual tone, there will be spurs, and that's to be expected because these outer ones are in a different pre-selected filter most likely. So it's much easier to get rid of them and much easier to get rid of the images and the spurs of this particular architecture. So we really need to zoom in around it and see the spur response at that point. And zooming closer, you can now see the spurs generated by the spectrum analyzer. These are of course not coming from our source, and they are all below minus 90 dBc because the fundamental signal is sitting at 0 dBm, or reference is at 0 dBm. Yeah, so they're definitely doing what they're supposed to. Now I can change the spur rejection. So if I go to bypass, you can see that they get worse. And that's also true because you're getting sweep speed back. So it is doing what it's supposed to do. And if I go all the way to enhance, we should get the best possible result. There you go. Yeah, they're even lower now. The close ones sometimes go around minus 90. Now, this is by no means a complete test because in order to really see the spur rejection of the instrument, you have to go across the entire frequency range, try all kind of different combinations of the inputs because the spurs can have some worst case scenarios. But I just picked randomly 3.2 and it is doing what it's supposed to. So I'm happy about that. Now let's focus on IM3 intermodulation terms and OIP3 measurement. So now we need to create two tones, and we can certainly do this using the Rohde & SMW-200A using both of its channels. Because what we can do is we can generate one tone here and an offset tone here and then combine them into a power combiner with some isolation. What this will do is that it would create an extremely clean two-tone signal because the interaction of the two sources are minimized because of the isolation of the combiner. We get a really nice signal as a result of that. And I've taken the output of that and I'm putting it through the FSWP so we can get a reference measurement. So now we can see the two tones and appreciate how good this technique is for generating really clean intermodulation products. So here are two tones. They're centered at 9 gigahertz. So this time we're choosing a different frequency so we can try our spectrum analyzer at a much higher frequency. And here are the two intermodulation terms. If you look, they're at minus 90 dBm, while the main tones are sitting roughly around 0 dBm. So the third order intercept point here is 45 dBm, so extremely good. That means that we should be able to easily measure the SAE-200 and see if it has any additional limitations. Now it is important to appreciate that the FSW can make these measurements under careful considerations. So for example, its own internal attenuation, is set to 25 dB. If I change that, these intermodulation terms are going to get worse. So with every spectrum analyzer, you do have to do some optimization to get the best dynamic range from it, and we're going to do the same thing with the SAE-200 too. And here are our two tones, and you can see that we have our intermodulation terms, which are quite a bit larger than what we were looking at on the FSW, and this is the importance of adjusting your instrument's front-end settings to get the best out of them. So right now my reference level is set to 0 dBm, the gain strategy is set to low noise, so not prioritizing the amount of harmonics there are. Let me also go over here and put the spur rejection on enhanced, just so that we can get rid of some of the additional ones over there. Now look what happens. If I just change the reference to 10 dBm, we're going to get some front-end attenuation, and look at what happens. It's a huge difference in the IM3 tones. Now they're sitting minus 86 dB with respect to the input. That's almost as good as the FSW by changing only one parameter. So you do have control over the reference, the gain, the attenuation, the preamplifier, and low noise, and all those conditions. Now if I just change that to high linearity, I suspect that I should be able to change this back to 0, and I shouldn't suffer so much of a result. Yeah, like you can see, it's considerably better than what it was before just by changing the gain strategy. Now, I understand what they're trying to do, but I prefer perhaps a bit more clarity so that the user really understand what is actually changing. And I think a block diagram will probably solve that. Knowing individually what is going on internally will help that, but it's definitely capable of generating these really nice results. Now, it does have its own internal IM3 measurement capability as well, and let's see if it does anything better. So enabling the IM3 measurement, you can give it a standard frequency, give it a span, and then it will automatically pick up the tones and then give you the OIP3 measurement. Most spectrum analyzers nowadays can certainly do this without any issues. And after it does that, it gives you a report where all the tones are and all the power is, and it's giving me right now an IP3 of 38 dBm or so. But can we make it better? So this is under this condition, the condition of high linearity. Now this is going to have exactly the same effect as it had before. Now I'm not sure why this is running so much slower than the spectrum, because the span is exactly the same, but it takes that quite a bit. I think it has to do with the fact that the video bandwidth and resolution bandwidths have changed a lot in order to be able to get a really nice low noise floor in this case. But look what happens. I'm just going to change the IF gain by 1, from 2 to 1. Now we wait a second for it to update this result. Let's see what it comes up. Look at that. Look, it went to 41 dBm. That's significant, right? It's almost twice as much in terms of power. So yeah, you do have to play with these parameters, but it's nice to see that, yeah, it meets its specification. You just have to be a bit careful on how you use it. So for our next experiment, let's use an ISM band transmitter with some impairments in it and connect it directly into our spectrum analyzer, leveraging its real-time capability, and see if we can analyze some of the issues. So in our regular swept spectrum, we can see the main tone coming out of our transmitter, and occasionally you see some activity here on the corners. Now, because we're in the ISM band, and that PCB you just saw is completely exposed, it's going to pick up Wi-Fi and Bluetooth and everything else. My phone is sitting next to it, and it's just picking up a whole bunch of garbage. We're not interested in those. We're interested to see the quality of this tone. Now, in a swept spectrum, it all looks pretty fine, and I can sit here watching this for a long time, and it looks stable, but actually it's not. And if you go under mode here, and go into real-time spectrum analyzer, looking at it in exactly the same span, if you pay close attention, you can see occasionally something showing up over here on the side. So let's go under graph here, and let's add a spectrogram on there so we can have that view. We can also change the afterglow. Afterglow is basically the persistence of how long some of these artifacts remain on the screen. And I can go ahead and change the afterglow, and let's put it all the way, let's say, up to here. Now it becomes a lot more clear that something indeed does happen to this. And if I go all the way to the right side, these just remain. And it's going to continue building up. So let's actually keep it like that for a second. If you look carefully, you can see that there is a jump in frequency. But this jump is very infrequent. And that's why it's so hard to catch in a swept spectrum. Our Wi-Fi and Bluetooth activities and everything else shows up quite a lot as well. So under this condition, with the Fourier transform that we have a probability of intercept of 16.67 microsecond. Now in this mode, I do have control over the bandwidth. Actually, I can click over here and change my span here. We're looking at an analysis of 100 megahertz or so, which means that the instrument is capturing 100 megahertz of actual spectrum, taking a Fourier transform and displaying it. Now, what I would like to see, which some of the competitors do, is a better control over how the Fourier transform is handled. Now, I don't see that here in any of the options. But what you want to do is to be able to control, for example, how many overlapping sections the Fourier transforms have compared to the previous captured window. which can be really helpful to identifying some of these effects. Now, if you look at the spectrogram, you can see these events that are passing by every time that this frequency jumps to the new point and coming back. And these are 1.27 seconds apart. So if you think about it, the duration of that shift in frequency relative to the actual time scale is absolutely tiny, which is why this probability of intercept calculation is really important. It tells you how likely you are to actually catch an event that's of this duration. So yeah, some modifications to the FFT would certainly be helpful, and here you can adjust things like resolution bandwidth. So for example, if I increase my resolution bandwidth, you can see that I can reduce my probability of intercept even lower at the cost of spectral resolution. So I no longer have that really fine differentiation between the points. So this is a balance that comes in with any real-time spectrum analyzer, but some more control of the Fourier transform here would certainly be really helpful. Aside from that, it behaves relatively normally like anything else would. Another thing you can do is you can record this. You can record this entire spectrum. It will stream it into your hard drive, and then you can analyze it yourself with a different software. We'll talk a little bit about that later on. Now, in terms of triggering here, it can be really helpful, but in this situation, the triggering can only be done on the level of the signal. It cannot be done on the frequency. Now, these are all possible to add to the software. It's just a matter of writing the code to trigger on different events that are visible within the spectrum you're looking at. Now, this does have an IQ streaming as well, which we will take a look at next. But yeah, this is a nice feature, what you would expect from a real-time spectrum analyzer. So let's try out some of the triggering capabilities of the instrument. So I'm going to generate an AM modulated signal, and at 14 gigahertz, I'm going to pass that directly into the instrument, and let's see how the software handles that. So now back onto the swept spectrum here, at a center of 14 gigahertz and a span of 20 megahertz, we can see that the amplitude is jumping up and down. And that tells us immediately that there must be some kind of an AM modulation or some AM effect happening on this waveform. Now we can, of course, use the real-time spectrum analyzer to get more insight on that, but the instrument does have a mode called power detection. In this mode, when you enable it, it plots the power of the signal at the center of the band as a function of time. So whatever that you have in your analysis bandwidth, it's capturing that power and plotting it as a function of time, which can be really helpful to find things like small power pulses or glitches in power. It should be very easy to catch that. Our analysis parameter here is 61 megahertz, which is more than enough for the kind of waveform that we are trying to capture. Now, this is a free running waveform, of course, as you can see. But we can introduce a trigger. There are several different triggers that are actually available in here. The level is the one we are looking for. Now, as soon as you add the level, you can then define the pre-trigger, post-trigger time. You can even re-trigger after an initial trigger event. But we have many trigger events anyway because it's crossing this line many times. And you can then define your level. So if I put this level above the trigger, it would behave basically like an oscilloscope. You're just looking at the power versus time. Now, if you look carefully, you can see that there are sometimes these vertical lines that appear. Now, they're very hard to catch. Actually, you can do a single, but I can't catch it on a single. I've done it many times. I haven't been able to catch one of those events, and I think it only happens in continuous mode. So you may think that, well, this is maybe directly from our source, but it's actually not from the source itself. I think this is a problem with a buffer overflow inside of the SA firmware that I think they can fix. Let me show you what I mean. So I've gone ahead and I have disabled the AM modulation. So this is basically now a continuous CW waveform. There is no glitches, there's nothing happening on it, but every once in a while you can see that we're catching these little glitches. Again, I suspect that this is a buffering issue. At some point, some samples must be lost, and it's just generating these nulls in there. You can see that they go down to below minus 90. So that's most likely just an arithmetic error. So hopefully they will fix that, because it does interfere, of course, with this power detection. But aside from that bug, you can see that you can catch these kind of waveforms fairly easily. Let me turn the modulation back on. You can see I'm looking at a really long time scale, and there are indeed glitches that are happening, and it's very periodic. So yeah, it's definitely some firmware issue, but this can be very helpful. For example, if you have some PAs that are having a burst of output power, you can couple that into the input and catch exactly what duration those pulses are. And to demonstrate that point further, here's an example of a pulsed output from a power amplifier. This is again at 2.4 gigahertz. These pulses are 10 microseconds wide and 90 microseconds off. So yeah, these are capturing them really nicely. And by playing with the analysis bandwidth, you can find the exact transition characteristic. And the smallest pulse you can detect will be determined by the maximum analysis bandwidth, which is in this case can be up to 100 megahertz. Now, if I zoom in further and further, you can see that as you zoom in, you can get some insight into what happens during these transition points. So there's a tiny little glitch at the very end of it, a little ringing before it turns off, has to do with how the actual switching happens. But by playing with the bandwidth, you can measure exactly the rise and fall time. So this is a really powerful tool for analyzing these type of events. So next, let's take a look at an unknown signal sitting in the band. See if we can decipher it and figure out what's going on directly by using the IQ streaming portion of this tool. So here's our tone. Let's do a peak search on it. It's jumping up and down. It's sitting at around 14 gigahertz. No problem. We can put the center frequency at 14 gigahertz in swept mode, and we can reduce the span. Let's see what do we see here. There it is. Let's do another peak search. Okay, so we do have our tone quite visibly appearing in the middle, and then we do have this sync pattern around it. Okay, let's decipher this. And we can access the IQ streaming by going through mode and IQ streaming, and I really like the way they've handled these sub windows. In this mode, at the very top, we have the entire captured buffer, which is their trigger event. So you can see it goes up to 1 millisecond. Within it are two of these windows that you can put anywhere you want during this duration of captured waveform. And within these windows, the instrument will calculate your spectrum as a function of dBm and IQ as a function of time. And that way you can see both of these events completely independently within the captured window, which is really nice. Right now, the maximum power versus time represents the total amount of power captured within this duration. And it's really low, and that's because our center frequency is at the wrong place. Let's put that at 14 gigahertz. There you go. We see our Fourier transform calculated down the middle, and this is exactly the same as what we were seeing here, except now we're capturing it in a streaming mode, so we can analyze it much more in detail. This is not in swept mode. Now going back over here, I can change the entire duration. For example, I can go down, and I can change my entire trigger duration to be much longer. So here's 1 millisecond. For example, let's make it 4 milliseconds. And you can see that the width of these windows are now much smaller relative to the total time. I can adjust these, and I can make them longer. I will be looking at the longer duration of both of these waveforms. We also notice that the power is constant as a function of time. And that tells us something very important. It means that whatever signal is coming into our spectrum analyzer has an average power that doesn't change. And that's pretty important too. Now, you can adjust these by grabbing them and moving them around, or you can adjust them by just simply going to their individual submenu. For example, the Fourier transform in here represents both the duration as well as the number of FFT points. So let's change the duration to something round, like 300 microsecond. As soon as you do that, you can see that this is now 300 microsecond within a 4 millisecond captured window. And I can change the FFT size to 8192. You can see we have much better spectral resolution. So it's really nice and intuitive. But what is actually happening here? Let's take a look at this IQ versus time at the bottom. Let's zoom out. So we can go under that IQ versus time menu, and you can capture longer and longer and longer duration. Look at that. We do have this slow drift up and down with a square wave looking thing down the middle. So what's going on? Well, let's think about this for a moment. Our transmitter and our spectrum analyzer aren't coherently locked together, which means that their absolute center frequencies aren't the same. The transmitter is sending something close to 14 gigahertz, and the analyzer is analyzing near 14 gigahertz. Now, we may be off only by hertz, in tens of hertz, for example, and this slow drift could be the frequency offset. So if I want to analyze that more effectively, I have two options. I either lock the spectrum analyzer and our source together at the same time, or I would offset this in frequency. If I were to take this and move it here by changing the center frequency of the spectrum analyzer, I will place this in the upper sideband, and I will create my own quote-unquote super heterodyne down converter. And then I can look at the waveform in a much more clear way. I won't have this slow drift anymore. Let's try it out. It will become obvious when I change it. So instead of looking at exactly 14 gigahertz, let's look at 14.01 gigahertz, just 10 megahertz away. Now this is going to sit a little bit off, and our carrier here is down the middle, still 14 gigahertz, but we've moved it a little bit. So now let's go and change that. Let's go over here and change this scale here, put it 100 millivolt per division. Okay, looks very different now. And let's zoom in now a bit more. We can use also the zoom function to further get insight into what's going on, and bring this down here, and let's do a single capture. Look at this. So what we're looking at are transmitted bits. these are when the transmitter is transmitting a 1, and these are when the transmitter is transmitting a 0. The fact that there is a sinusoid envelope within this is because we've offset this by 10 megahertz. So the tone in here is 10 megahertz. We're just looking at that offset to make it easier to see what's going on. And now, if you know your modulation, this is clearly an amplitude shift keying modulation, where at 1 we're sending full power, and at 0 we're sending 50% of the power. And then by looking at the time scale here at the bottom, we can also capture the bit rate. So if we're looking at one of these, over here, we can look at the length of this one, the smallest pulse, for example. We can search for it, and we will conclude that this is a 14 gigahertz carrier, amplitude shift keying modulation, with a 50% modulation depth at 1 megabit per second. And all of that is possible by just simply analyzing this very quickly. Now, because we know this is ASK, amplitude shift keying, we should be able to add another plot, which is power versus time. And we should be able to see the same thing now as an envelope of the signal. Now, one other small point, I did notice something a little peculiar about this, and I think this is related again to the buffering issue. If you look at the very end of this, you can see that this power begins to drop occasionally, this waveform, and that's not real. Again, I think it has to do with what happens when the buffer is full. They need to take a look at that a little bit more. And if I change my IQ sample rate, once I go below a certain amount, I begin to see some kind of images coming in. Look at that. Yeah, there's some weird artifact happening here on the right side. This is, again, of course, not real. I wonder if it could be some kind of aliasing that's happening. But yeah, these things need to be taken care of a little bit better in the software to avoid this kind of confusion, because this looks like there's now two carriers because one image is folding on the other side. This can be easily fixed. Just requires a little bit of finesse on the actual software. So let's go ahead and add another window to this. We can do that by going over here. And now we can add the power versus time. And this should give us a nice envelope. Now it's sitting all the way up there. We can, of course, adjust that by just selecting the graph. Let's change the scale to 2.5 dB, and let's put a 10 dB offset on this. And here it is. These are our bits coming in exactly the same way. If I do a single, you can see that these are the envelopes of these waveforms. So that's quite nice, and all of them are completely independent, so I can move this around. You can see the individual bits show up. Of course, I have to let go of the mouse, unfortunately. But yeah, I can grab it and make it longer. You see more bits. Make it smaller. You see less bits. And then, yeah, that's exactly the envelope. Those are the bits. You can easily capture them. And you can see also the modulation depth by just looking at this. Now, there is a triggering function just like before, but I can't quite get it to work. So, for example, if I go level here, and it just pauses. If I go -5, oops, that's wrong. Let's see if I can put 5 in here. Yeah, you can see that it kind of hangs around. It doesn't let me actually enter the value correctly. But if you do it a couple of times, you might be able to catch it. There you go, -5 dBm. So then it pauses for a while. And I don't see the line here, which I was seeing before when we were looking at this other mode. When we were looking at the power detection mode, it was working correctly. But here there's some bug going on in here. And when I go back from level to bus, I should be able to, yeah, there you go, I get this error. And yeah, there's some minor bug in this. I'm sure they can fix it. And once I press OK, it puts my frequency, center frequency, back to 1 gigahertz. Yeah, there's a little tiny bug there. They should fix these because the software is otherwise quite good, minus these few bugs. There's also digital down conversion you can do. There is a demodulation of AM and PM, but yeah, those are going to be very similar. But this software tool, the way they've managed to do it, is really quite intuitive. You can select individual waveforms, you can put different things, everything is calculated separately and really quite fast. The computer I'm using is not a very fast computer, but it's doing a very good job doing this. And we've really only scratched the surface, because you can also record and play back the waveforms and analyze them back in the software. But there's also an extensive API, and with that you can write your own code and do anything with the captured waveforms. And this is compatible with several other software, so you can use other people's tools to analyze these kind of waveforms as well, basically having a complete software-defined radio in the span of 20 gigahertz with 100 megahertz of analysis bandwidth. The reason I focus on this software is because this is the entry. This is what they give you, and that's the lowest effort to get started using the software. And that's why I also focused a lot on its performance metrics, because once you capture the waveform, you have complete freedom, but it's important to understand the actual performance of it in the hardware point of view as well as the software. And there you have it. I hope you enjoyed this extensive review of the SAE-200, taking a look at its architecture, how it performs under various conditions. There is even a 40 gigahertz version of this instrument in the same form factor, I believe, which maybe we'll be taking a look at in the future. As always, let me know what you think in the comment section, and I'll see you next time.